So, the chain rule is going to open up a lot of possibilities for us now. That's the good news. Or maybe that's bad news too, because now we're going to have even more, derivatives that you can know how to do. This can be a little challenging. All right, so please, don't fret too much if you're having some trouble with it. It's okay. This is a bit of a challenge, right? So don't fret too much here. All right, now we're going to do this little kind of exploration. I'm going to get us kind of kicked off here with the first one, and then I'll kind of have you guys kind of go through the next 4 here. All right, so looking at this first one, okay, and the directions are very similar for 1, 2, 3, and 4. All that really changes is the function that I'm giving you. So the first one, it says, use the basic power rule to find f prime of x given f of x equals x plus 3 squared. Next, multiply, actually I might do the first 2 with you and then have you do the next 2. But anyway, next multiply out and then differentiate. Do you notice any similarities or differences? So what I mean here is that we're going to be doing this, we're going to be doing these derivatives kind of 2 different ways. The first way we're going to do it is kind of the way we want to be able to do it. So what do I mean by that? Well, if we have f of x equal to x plus 3 quantity squared. Okay, those of you guys that already know the chain rule, kind of I understand, don't give me what you know the answer is, but, right now, we're going to do it kind of the more kind of intuitive sense. If we want to take the derivative of this thing as it's currently written, what's our kind of natural inclination to want to do here? What do we think feels right to do here? What should we do? Okay, FOIL it out. But what I mean, okay, so let's say if we want to take the derivative as it's written without rewriting it. What do we want to kind of do here with, for example, this power of 2? What do we want to do?
Throw it up front.
Bring it out front, right? Leave the x plus 3 in there, and then lower the power by 1, like that, right? Don't we want to do it that way?
Yeah.
Okay. Well, so that's kind of fuzzy, though. We're not really sure. Mr. Witt's saying, what do we feel like doing? Not what we should do kind of thing. So, and that's not, normally we would FOIL this out. And in fact, let's go ahead and do it the right way, right? The way we know is correct by FOILing it out, right? As it's currently written, we're not sure if this is going to be right or not. But let's do it by FOILing it out. So that would become x plus 3 times x plus 3, right? Which is then x squared plus 6x plus 9. And rewriting it that way yields f prime of x equal to 2x plus 6. And if I factor out a GCF, it yields 2 times x plus 3. So wow, they look identical, don't they? In fact, they are identical. So it's wow, maybe we've stumbled across a way to take the derivative here without having to FOIL it out. Right here, it's kind of nice. We didn't have to FOIL this out to get this answer. Here, we did have to FOIL it out to get the same answer. So maybe we don't need to FOIL. Maybe we don't need to. Maybe. All right? So questions on any of that?
You're lying. You're giving me false hope, Mr. Wood.
Well, but I am and I'm not. Okay, so let me show you here.
Which one?
Let's take a look here. So let's try this next one. So now, use the basic power rule to find g prime of x given g of x equals 2x minus 1 quantity squared. So let's say g of x here, okay, equals quantity 2x minus 1 squared. Using, and I'm going to put, sorry, I should put this f prime of x in kind of quotes, air quotes. I'm maybe this is f prime. We'll see, okay? Same thing here. We'll call this g prime of x. And maybe it's g prime of x. We'll see. So again, using just our power rule here, what should we do with this 2? Bring it out front, so it'll be 2 times 2x minus 1, and then lower the power by 1, so to the 1. So 2 times 2x minus 1 to the 1. Okay? It's maybe that's the faster way to do this. Why have we been FOILing it out when we don't even have to? Well, let's now take a look and see if it is exactly the same thing like that first one. So it's going to be 2x minus 1 times 2x minus 1, which is what? 4x squared minus 4x plus 1? Yes. Okay. And then if we take the derivative of this, we know this derivative should be right. right? When we FOIL it out and take the derivative, that's what we normally have done, so we know this derivative has to be right, must be right. So what's the derivative of 4x squared minus 4x plus 1?
8x.
8x minus 4. Which again, we have a GCF here. Let's pull that GCF out. And what is the GCF here? 4 times 2x minus 1. Oh, interesting. So here, we've got 2 times 2x minus 1, using the kind of like way we feel like should be right, but here, using the actually correct way, we get 4 times 2x minus 1. Okay. So they're not, odds not equal, but they're close, right? They're still kind of close. Go ahead, try 3 and 4. Go ahead and try 3 and 4. Okay, try 3 and 4. Brittany, don't tell him what to do. He's got to think about it. All right, so go ahead, Brandon, try 3 and 4, and then Brittany, you know, but don't tell him. Don't give it away. Well, if he doesn't see it, that's okay. Just let him think about it, okay? You must struggle to learn. This is my accent. This is my normal.
Different accent.
An American
Russian.
American accent.
Russian accent the whole class. That's my favorite accent.
Mathematical equation.
It's my favorite.
Oh, you forget who it was?
If I got to learn
Who asked you? Who told you? Oh, okay.
instantly, it would be
Interesting.
I wouldn't run a Russian.
Russian. I would learn Russian.
I probably wanna
Like if
stop
I just got to
accent.
download a language into my brain, it would be Russian.
Why? I would have the
Russian's
Chinese.
awesome.
Can you do my club team code Russian?
Oh gosh.
We got the differentiate.
I don't
want to.
Shh, come on, guys. 3 and 4. Let's get these done. Come on, 3 and 4. I'm going to do them real quick too. Yeah, 3 and 4, please. 3 and 4. Go ahead and do the rest.
Then prime of x, x cubed plus x.
You have time to watch a 2-minute trailer? 2 minutes.
This is gonna have to do with the highest degree in the front, isn't it?
We'll see.
Let's see how this is gonna go. That's me. You're making that. Sounds like a bird. Whistling? Well, I'm smiling, so I can't do it. Go for it. Oh, great. That's a big number. Yeah, I'm not pulling that out. I ain't doing it. Anna. Dude, I know you can hear me. You're smiling at me. Can I have
She's busy working, Austin.
I need my sweater back. You should have fine.
Water.
Because that has nothing fun. Figuring it out, guys.
That is disgusting. What'd you do for last one? Our big ass answer.
Yeah.
It's gonna be nutty.
2x times
That's the old way out.
2x
Yeah.
times quantity 3x to the 4th plus 4x squared plus 4.
What? Oh yeah, true. You can take a 2 out of that as well.
Alternate interior angles.
Looks like we're just about.
Hey, look, angle side to side.
Theorem is not an actual theorem.
That's the biggest thing ever. Theorem that makes you bad work.
If you ever use the inappropriate word for the wrong, you are getting points.
This is really nice right here. It's like a camel word.
Until like overheats.
Yeah, and mercury everywhere.
Like, what do you mean?
Yeah.
He said that we would get
It
in
was
trouble.
very funny.
He said that we would get in trouble if we used the ass theorem.
You just tell your kids not to use the ASS.
Well, the thing is, like, it literally is. It is not a triangle
Yeah, I know.
congruence. Like, it's not just like math teachers are trying to like, you know.
Like, if you use the theorem that makes an inappropriate word, you will get points off.
No, I have heard that. Yeah. Like he takes away points if you use it, right?
Yeah.
Yeah. It might have been. Yeah, it might have been more.
I tell all my geometry students, and they I think they seriously put it down. I'm like, come on, guys, do you see the word you're spelling? I told you, like, it's usually like you should see that and be like, oh wait, Mr.
Write the word
says
ass.
not a
It
congruence.
doesn't work.
Right. No, yeah.
You don't like say that.
Anyway, okay. Shh. Let's come back together here and see what we've got. So, the first two we've already kind of gone through. Let's take a look at number 3. So number 3, hopefully, again, using this kind of like method that we really would like to work, right? Just bringing that 2 out front and leaving it 2 times 3x squared plus 1, comparing it to the actual derivative. Again, we see there's the 3x squared plus 1, but instead of a 2, we have a 12x here. So again, it looks like we're slightly off. Same thing here, right? Here we have the 2x minus 1s, both to the 1 power, but here's this 2, this is 4. The only time where it really matched up was the very first one. All right, and then we go to the very last one here with a little bit of manipulation. You can actually see a closer relationship here. So you can see that when you take the derivative of this, as we think we should, bring the 2 out front, lower the power by 1, and if you factor out a GCF from that, you're left with 2x, x squared plus 1, which is right there. All we're missing there is the 3x squared plus 1, right? Like it's like almost the same exact thing, except it's just missing a 3x squared plus 1. If you could actually factor this little polynomial here, and it gives. So we're missing that. So it's interesting here. So let's see. All right, again, comparing these. So let's maybe we can find a pattern in how things are, how they're different. Like how we're like the thing that's missing. We can see something. So here, they're exactly the same. So there's no difference. Here, how are these two things different? What do I have to do to this thing that I want to work? What do I have to do to this to make it match what I know is true? Multiply by 2, right? Okay. For number 3, to get from the one that I want to work to the actual one, how do I have to change that one? Multiply by 6x. Excuse me. And then for this last one, to get it to work,
A lot.
what do I have to multiply this one by to get this? 3x squared plus 1. Where are we getting this times 2, this times 6x, and this times 3x squared plus 1?
The first term.
What do you mean by the first term, Emma?
3 is just a derivative of the thing in the parentheses.
Yes, it's a derivative of 3x squared plus 1. Does that hold true for number 2?
Yeah.
Is the derivative of 2x minus 1 just times 2?
Yeah.
Yeah. Is the derivative of x cubed plus x, what's that? 3x squared plus 1, which is the thing we're missing. So it looks like only thing that we're missing here is that we're forgetting to multiply by the derivative of the thing inside the parentheses, and that would then yield the correct derivative without having to FOIL out ahead of time. Okay, so that's the whole point here. Without having to FOIL, we can actually take the derivative of this thing. Could we still FOIL this and then take the derivative? Absolutely. Absolutely. Yeah.
So, oh wait, never mind.
Who said that?
I just figured out my own
It is too much, Brittany, you're right.
I was going to ask, why don't we have to do that for the first one, except then I realized that derivative of the first one is just 1.
No, but that's a great point, though. Exactly right. So if we look back to this first one, which exactly matched up, Ryan's question was, why doesn't that work for the first one? But then he realized it does, right? Because what's the derivative of x plus 3? 1. So it's going to be this times 1 gives you that. So there's no need to. Okay?
This looks so simple right now, because I know you're going to make it way.
Well, I mean, but that's the basic idea of the chain rule. Okay, so flip your papers over. So, well, actually, sorry. So, when differentiating... Shh, listen, please. When differentiating functions with inside parts and outside parts, we must use the chain rule. What do we mean by inside and outside parts? Here, we had an inside part, x plus 3, then being squared by an outside part. So we had something in something else, and so we had to use the chain rule. Here again, 2x minus 1 was being squared. So we had to use the chain rule, or FOIL it out. So there was nothing inside something else. Here, same thing. 3x squared plus 1 was squared. This was something inside something else. We had to use the chain rule, or simplify it so that there's not something inside something else there. Okay? That's the idea. So, let's go and actually talk about what the chain rule is. So, the chain rule. If y equals f of u is a differentiable function. Yeah, I know. Some of you guys are thinking, yeah, right now I'm going to tell Mr. Whitmire F you for making us learn this. All right. If y equals f of u is a differentiable function of u, okay, so that just means that this little u here, okay, we can take the derivative of f with the u in there, and we'll say that u is equal to g of x. So really, instead of writing y equals f of u, equivalently, I could write y equals f of g of x. Y equals f of g of x, right? I can put the g of x inside the function f there. Okay. So, and u equals g of x is also a differentiable function of x. Then y equals f of g of x all right, so again, basically we're kind of breaking the two parts up first, and we're going to put them together. So we're saying basically f is a differentiable function of u, g is a differentiable function of x, then y equal to f of g of x will also be a differentiable function of x. So plugging a differentiable function into another differentiable function will still yield then a differentiable function. And, alright, so here's like what we were finally all building up to. So we have two functions. One is kind of plugged into the other one, and that creates this new kind of function. The derivative with respect to x of f of g of x is equal to okay, notice here very importantly, g is inside of f. F is outside on the outside of g. All right, g is within f. The derivative of this is going to be the derivative of the outermost part, f, leaving the g of x alone. Okay, right? That's kind of like how we did, oh, it's on the back, so I'm just going to do it this way. That's kind of like how we did it here, right? We took the outermost function here, oh, you can't see it, sorry. We took the outermost function here that was being squared, and it was like something squared. We took the derivative of that outermost layer. What's the derivative of something squared? 2 times that something to the first. So we just took the derivative of the outermost piece. We left what was inside alone, 2x minus 1, but then we have to multiply, like we saw, to multiply by the derivative of what's inside. So here we had to still multiply this derivative by the derivative of what was inside, so another 2. Okay? So it's the derivative of the outermost layer, leaving what's inside alone, times then the derivative of what's inside. So in this specific case right here for number 2, the f function is the something squared function. The g is 2x minus 1 because that's inside being squared. So the 2x minus 1 is like g, the f is like the something squared. And so the derivative of something squared is the 2 times that something, times then the derivative of what's inside, which is the derivative, this is 2. So that's why we missed the times 2 there. It should be a times 2 in there. Okay? Fix it. That's the idea. Okay? Or, if you want to think it in terms of y prime equals f prime of u times u prime. You can think of it that way too. Okay? Using the f's and the u's instead. And again, everyone's like, yeah, fu, Mr. Weird. Got it. Point noted. Okay? So, let's use the chain rule to find the derivative. Let's do it. Make it so. All right, so prior to today, could we, with the tools that we had, could we have done this derivative prior to today? We could have. What would we have to do, Brandon, if we were to use the tools prior to today? What would we have to do?
We have to FOIL all that out.
We have to cube this out,
Yeah, and then we have to do the power rule for
and then just, and then simplify, take the derivative. Yep, exactly. So you can see, right, that's a little bit of a daunting task. Cubing this out, or if this was like to the 10th power here, that'd be like, as Brittany said, that's too much, right? So that's not what we want to do. We're going to save some time here by using the chain rule, okay? So identifying the chain rule. Let's go back to kind of how we have to kind of be able to see the chain rule here. We have a function, 3x minus 2x squared, within a function of something cubed, all right? So what is the outermost layer here? The cube, right? It's this thing's inside the cubic. So our f is this cube. When I go to take f prime of x here, okay, I'm going to take the derivative of this cube first. So what's the derivative of something cubed? 3 times that something to the 2 power. So we just did this piece right here. We just did that piece right there. Okay. The something cubed became 3 times that something squared. So we just did this part of the chain rule. Now, are we done?
No.
What do we still need to do? Multiply by the derivative of what? The 3x minus 2x squared, or I would say the derivative of what was inside. So in this case, what's inside is the 3x minus 2x squared. So times the quantity 3 minus 4x. And we're done. We've taken the derivative.
So we just leave it at that?
So if you want to just stop there, yeah, that's all you have
Is
to
that
do.
the answer
You
on
do.
them all?
I would recommend actually against foiling this out. It's rare that you would be expected to foil that out, I think, for multiple choice. Because I think that kind of almost unsimplifies it if you think about it by foiling things out. Unless you maybe need to combine like terms with some other stuff, you know what I mean? But like as it's currently written, I don't see any other way to simplify this, so I would leave it. So the answer here is going to be 3. I like to write it in kind of like order of power though. Okay, and so that's why I wanted to write. Okay. I don't know if that helps or not, but I just kind of organized. All right, so there's that. But we could do that before. Let's try another one. Any questions on that first one? All right.
I was like looking below that, and I thought you were like looking for a problem or anything.
Okay. How do we take the derivative? Or what do we need to do first here before we start trying to take the derivative? Yeah, so a square root is no good for us. It does not help us. So we need to change that square root. Instead of the square root of x squared plus 1, it should be the quantity x squared plus 1 to the what power? 1/2 power. Okay, so remember that's not taking the derivative, right? That's not taking the derivative, that's just rewriting it, right? These are equivalent statements still. Prior to today, were we able to take the derivative of this thing?
Yeah.
How?
Never mind.
Yeah, actually, this one we can't take the derivative of using the skills prior to today because we can't like FOIL out something to the 1/2 power. So we actually can't do this one. Okay, as it's currently written. But we now know using the chain rule how to do this. So we'll say y prime equals. And guys, please make sure if you're writing y equals and you put your equals here and your equals there, and make sure when you're saying the equals that these things are in fact equal. And then when you go to take the derivative, actually write y prime and don't just put another pair. Don't just like leave the equal sign there and say that because that indicates to me that y is still equal to the derivative, which is not true, right? Y prime is what you're doing here. So please make sure you label things accurately. All right. So again, chain rule. What's the outermost function here?
1/2.
To the 1/2 power. So what's the derivative of something to the 1/2?
1/2 parentheses.
1/2 parentheses, yeah, x squared plus 1 to the negative 1/2 times the derivative of what's inside, so yeah, 2x. So the 1/2 and the 2 cancel. The negative exponent, we should probably simplify that. Where does that going to go?
On the bottom.
In the denominator. So it's going to be x over
Yeah.
x squared plus 1 to the 1/2, which is the same thing as x over the square root of x squared plus 1. Yeah.
Whoa.
Could I have stopped right here? Yes, but I will say this. One kind of simplification that's a common kind of simplification we should be comfortable with, Anna, is that negative exponents we should be comfortable with, like, manipulating those around. So that's why I chose not to stop and continue on there.
Do another one.
You got it. What's that?
I just thought it was interesting. And it's just X over the...
It is interesting, yes. And you'll see kind of like things like that show up. All right, let's try one more, or actually two more here. Yeah, two more at least. All right, so g of t. Change the variables up a little bit here. Uh-oh. I see a big division bar there. So, with the way it's currently written, if we want to take the derivative of this,
What do we have to use? We would have to use the quotient rule. Ugh. Don't want that. That's just gross. Can we, so we could use the quotient rule here. We could use the quotient rule, for sure.
What other options do we have? We could rewrite this using a negative exponent. We could say negative 7, 2t minus 3 to the negative 2.
Yes.
Now, with the way this is written, we don't have to use a quotient rule, and actually we don't even really need to use a product rule here. This negative 7 is a coefficient, right? So we can kind of just like bring the negative 7 along. It doesn't have, I mean, you could do a product rule here. That wouldn't be wrong. You could say negative 7 times this thing and then use the product rule. That's fine. But actually, since it's just a coefficient, like if there were an x here, then we would have to use a product rule for sure. Or sorry, a t. If there were a t here, we'd have to use a product rule for sure. Since it's just negative 7, though, it's like a coefficient. We can just kind of leave that out. So we'll take the derivative of this thing as it's written here. So again, what's our outermost function?
Power negative 2.
Something to the negative 2. So what's the derivative of something to the negative 2? The negative 2 goes out front. So negative 2 times negative 7, 14. Times 2t minus 3 to the what?
Negative 3.
Negative 3. Sorry, I gotta screw this up. Times the derivative of what's inside? 2. So we get what? 28 over the quantity 2t minus 3 to the third. 2t. Questions on any of that? Right? Let's do another one here. F of x equals 5 minus x quantity squared times 3x plus 1 to the third. We're ramping it up.
Oh, I don't like that.
So Austin, why do you say you don't like that?
Because we're going to have to do a product.
Because we have to do a product rule here. No way around it. We have two things being multiplied together, okay? So you got to use a product rule. And then within that product rule, we're going to have to also use the chain rule. So let's do it to it here, all right? So f prime of x equals, okay? I'm going to say this is my first and this is my second, right? It's important that we're able to kind of like break up our product into the two pieces here. So it's going to be 5 minus x quantity squared, that's my one piece, and the 3x plus 1 to the third, that's my second piece. Okay? So again, the way I do the derivative is I do the first times the derivative of the second plus the second times the derivative of the first. But you can absolutely do it the opposite direction as me, do the second times the derivative of the first plus the first times the derivative of the second. It's whatever you know, as long as you're doing the derivative of one times the other plus the other times the derivative of one, that's okay. Okay? But I do it always the same way because it just helps me to make sure I get it right. So it's the, for me it's going to be the first here, so it'll be 5 minus x quantity squared, 2. So I took, oh my gosh, I'm messing up already, sorry. The first, so 5 minus x, quantity squared, that was right in the first place, times the derivative of this second thing. So the derivative of something cubed is 3 times that something to the second power times the derivative of what's inside here, 3. Okay, so again, I did the first thing here, left that alone, times the derivative of the second. The derivative of this, you bring the 3 out front, lower the power by 1, leave what's inside, but then times the derivative of what's inside, so the 3 there. Okay, plus the second times the derivative of the first. So the derivative of this is going to be 2 times 5 minus x to the 1, so I'm just going to leave it, times, what's the derivative of what's inside here?
Negative 1.
Yeah, negative 1. Watch that. Yeah, sorry. Just a skosh. So again, if it were free response, you could stop here, and if you're like trying to find the value of the derivative, you could like plug in your x value here. I mean, you're good. But I want to show you guys how to simplify this. And actually, there's an easier way to simplify this. Shh. Listen, please. There's an easier way to simplify this than foiling this all out, and combining like terms. Look, we have two terms here, right? There's only really two terms because they're separated by addition. There's two terms. Do you guys see anything in common between these two terms? They both have a 5 minus x. So let's pull out a 5 minus x. Okay. What else do they have in common? How many 3x plus 1s? Yeah, we can pull out, this is 3x plus 1 squared, this is 3x plus 1 to the third, so we can pull out a 3x plus 1 squared. Now, if we do that, what's left over from our first term? A 5 minus x, and then what else? And then actually times a 9, I think, right? So 5 minus x times 9, plus what's left over from this second term here? 3x plus 1 and negative 2. So I'm going to put a negative 2 times 3x plus 1 there. Yes, and I would highly recommend you get practice at doing this because this is going to make your life a whole lot easier than having to foil this all out, combine like terms, and then factor it. This is so much easier when you pull up the GCF because look how much easier this is to simplify. Now all I'm doing is distributing the 9 and I'm distributing the negative 2 and then just combining like terms there. It's so much easier. So you still have to bring down those other parts. Don't forget those. And so let's see, I'll have 45 minus 9x plus negative 6x minus 2. And then let's see here, 5 minus x times 3x plus 1 squared. And let's see here, negative 9 minus 6 is negative 15x, and then 45 minus 2 is plus 43. Wow. Or as Owen Wilson would say, wow. Okay. So, look how helpful this was. The only other alternative that we would have here is to FOIL this all out, plus this all FOIL it out, combine all those like terms, and then try to somehow factor that. Instead, if we pull out the GCF, what we're left with here is something very simple to then distribute, combine like terms, and there it is, factored all nice and neat for us without having to FOIL it out first and combine like terms.
Thanks,
That's it. That's right. It's very convenient. Okay. Questions on any of this? All right. So, I want to also then talk about the general power rule now. General power rule. So we learned the power rule before. Now we're going to talk about the general power rule that's like more generally useful, right? So if y equals
General power.
So if y equals now not just x to the n, remember our old power rule was if y equals x to the n, and then we did a derivative of that. Now we're saying if y equals some function to the n power, where u is a differentiable function of x, okay. Obviously, we have to state that u is differentiable. If u is not differentiable, then we can't take the derivative of it, so we kind of like are stopped there in the first place, right? So that's why we have to state that u is differentiable. And n is a rational number. So n can be a fraction now, right? Rational number, which we already seen that, though. Then the derivative with respect to x of u to the n
writing, and I realized you're like writing on.
Yeah.
Oh, I'm sorry.
I would start writing the derivative.
Then symbols now.
I ended up doing that too.
That's what I do.
But now I love when I write it.
No, I'm better than you.
What would this be? What's the derivative? What will we say is the derivative of u to the n? N times u to the n minus 1 times u prime, or the derivative of u. So we'll say u prime.
What?
If we have a function that we're just generically calling u. So remember, before, it had to be x to the n, the variable x to the n power. Now I'm more generally saying, let's just say we have any function u of x, okay? Yeah, u prime, Then u, that function u to the n power, the derivative of it will be n times u to the n minus 1 times then the derivative of what's inside. There's the chain rule showing up there, but it's the general power rule. Okay, general power rule. All right. So I'm going to give you guys one to try here. All right. Here we go. Find all points. So try this one. Find all points on f of x equal to the cube root of x squared minus 1 quantity squared, for which f prime of x equals 0, and those for which f prime of x does not exist. So you're finding me two sets of answers. Find all the points on this function for which f prime of x equals 0, and find all the points on f of x for which f prime of x does not exist. So two sets of points. The x values, I guess, is all I really want. Okay. So, if we look here, just let me show you the graph, and I'll let you guys actually calculate this by hand. All right, let me do this. Let's zoom in a little more. There's the graph of our function. All right. So, if this is f, anyone want to guess or make a a conjecture about where we can expect to see what x value will f prime equals 0? Not a negative 1 and 1. Where should the derivative of this equal 0? At x equals 0, we should expect a kind of horizontal tangent line right there, right? Let's do a horizontal slope. So maybe we're thinking x equals 0 should be where the derivative equals 0. Where does it maybe look like in this picture that the derivative would not exist? Why at 1 and negative 1?
Because
what do you see visually there? It's pointy, right? The slopes are suddenly changing from negative to then flipping over here to positive, and then negative to flipping to positive there, okay? So that's right. So actually now do it. Find the derivative, see if you can then, guarantee that the derivative does equal 0 at 0, and see if you can guarantee that the derivative does not exist at 1 and negative 1 once you've taken that derivative. So actually do the derivative, yes.
So made it to the x to the power of 1/3, so then can I put 2 and 1/3 together?
Yeah, yeah. When you have a power raised to a power, you can multiply the powers together.
Great. goodness.
That's right, so gotta use that chain rule.
Well, so, right away,
I don't know.
so how do you rewrite cube root? What exponent is that? Goodness.
Walk. Just walk.
I got that. Alright. So I don't know how to find the points where zero does not exist. Like, I mean, I can find the points where the derivative equals zero. You just set it equals zero.
Wait, for the derivative, did you get it because 4x equals 3 times programming? We take it in class, like last year.
What do you got? Because you assign the computer what to output. The computer has to be told.
Like imagine like that.
So it's not random if you're telling it what to do. However, if you use something that
Yeah, I was
always
just gonna
changes
learn this
time,
lesson, right, and then just only play.
like making.
I don't know how to find where it doesn't exist.
Still,
Oh, where
you
it
can't make- you can't
bottom
make- you cannot
zero.
program it.
Okay.
So like. Okay.
Yeah.
So.
That's what I'm talking about.
Derivative yet, right? All you do is rewrite that. So now you're ready to take the derivative though. So, what's the outermost function?
I don't understand.
Oh, nice part. You need what's inside at first. You only take the derivative of a layer at a time. So you take the outer layer, don't forget the power.
There should be.
How do you find them for the ones from?
Okay, but you said the denominator equals zero,
Yeah.
and no, you can't. And it just can't equal zero. Like x can't equal zero. So you should get three answers, and it's the two that don't equal zero.
I think I didn't.
Except I don't know how to do
What's the denominator already?
Yeah, like,
I mean,
Zero is.
I think that's supposed to be negative.
I don't know how I got this.
Water. Yeah, you're right. Probably.
Oh, that's right. That's still there.
Cube root.
Oh, you did.
I don't know why.
You're probably.
Hey, Anna, question? I'm sorry.
What's it?
Wait, can you get it?
Alright, so, the derivative here.
I don't know.
2x here as well. And you put it there, but put it up here too, because once you take the derivative, you get the full derivative. Okay, now, what is your, I would rewrite this. Well, first one, how much you're getting 1/3 power here?
Yeah, it is x.
Rewrite it as a fraction, right? Make that negative exponent go down to the denominator, which is fraction, you've already started here. What's x, where will it go?
And that's just x plus one x
On top, and then x minus 1 to the top, 1 to the bottom. And then I think you'll kind of get.
Well, I'll be able to help you more from there once you get to that point.
All right, how y'all doing over here?
Yeah.
Oh my God.
I got it too, because then you take the cube root of both sides.
Yeah.
I feel like I messed up right here. So, yeah, it's 2x.
And then you put the two. So basically, then you put the two. You make it a fraction. You put the two in the numerator and the 2x in the numerator. And you multiply those together. That's 4x.
2 times 2x over would be x like that.
And then 3 out front there.
Oh, you made it like a root.
Well. And
Oh
then,
yeah, I see. Yeah, 3. And then one's actually. Yeah, one's there, and then you change it.
Yeah, then I made it.
And then this is right, but you can do it here. How would you? I got a problem.
So 4x over 3.
How are we doing here? Oh, it's beautiful. That's a beautiful problem there, Emma. I know, you got Ariel and Star Wars on the brain. There's Ariel just thinking about Star Wars. Like, Star Wars.
Alright,
You know what the cube
then-
Why?
Yeah,
You
why?
take the cube root of both sides, and the cube root of 0 is 0.
So when does this equal 0?
Oh yeah, I see.
Plug in 0, you know when it equals 0.
But wait, I think I got them all right.
When it says equals
You have the points negative 1, 0, and 1, 0.
I got x equals negative 1, x equals
Correct.
1.
With.
0 and 1 and negative 1?
No, I thought
Yes.
Oh, and then,
So when I ask for a point, it actually wants X and Y coordinates as well.
So you probably should get the x and y coordinates, yes.
So it's correct, so once I get the X coordinate from the, here, plug it back to the original one.
So you have to solve when like the numerator equals 0 and the
Well, at 0, it does exist. It's just 0. Or, sorry.
or is it no, it's when the whole function.
0, but it's being
Like, so you get when the
oh, but a
function
cube root,
does
so
not
you think
exist,
cube root of
it's just the denominator.
yeah, it's just the denominator.
And then when the function
Okay.
is there, it's the whole.
It's the.
Real quick here, folks, let's take a look, see how we're doing.
All
right. So, the derivative, right, is the, obviously the most important thing here to get, right. So, but first we have to rewrite this. So, the cube root of x squared minus 1 quantity squared is the same thing as x squared minus 1 quantity squared to the 1/3 power. That 1/3, it's power to a power here. How do you simplify power to a power? Multiply them. So you get 2/3 there. So this is still, by the way, this is still f of x. This is not the derivative yet. All I did was rewrite. So this is not the derivative. So that's why I still have equals f of x. Now I take the derivative. So the 2/3 comes out front. Lower the power by 1. Leave what's inside. Then times the derivative of what's inside, 2x. Okay? That's the derivative. You must do this all in one step. Don't take it like piece by piece. You need to do it all at once. Okay? To take that derivative there. Don't leave that 2x out to like another step. It needs to come out and multiply right there, that first derivative, okay? And then we write it. So let's see, how can we rewrite this? Well, let's see, x squared minus 1 to the negative 1/3, where will that end up? Goes to the denominator. In with the 3, which is already in the denominator. This 2x is a numerator, it's going to be in the numerator up with the 2 here. So 2 times the 2x gives you the 4x, 3 in the denominator, and then cube root of x squared minus 1. All right? If you are uncomfortable with fractions, you're going to get comfortable with fractions. All right? You will get comfortable. Eventually.
You're going to be comfortable.
Question, Emma?
How did you get, like, from f prime to 4x?
So, again, it's a matter of looking at your exponents. The x squared minus 1 here to the negative 1/3. That's a negative exponent, so it goes in the denominator. We already have a fraction started right here, so it's going to go into the denominator with the 3. The 2 is in the numerator, but what else is going to go up there? The 2x, because 2x is really the 2x over 1, so it's 2 times 2, 4, and 4x then. That's the idea. Okay? If it doesn't have a negative exponent, it goes up into the numerator. Right? So there it is. How can we tell when this thing equals 0?
Numerator's got to be 0.
Right, so what do we have? What is this thing? Fundamentally, in its most basic, idea, it's a fraction. The only way that a fraction can equal 0 is when what part of the fraction equals 0?
Numerator.
The numerator. So all we have to do is set the numerator equal to 0, and so that just gives us that f prime of x equals 0 when x is 0. 4x is equal to 0 when just x is 0. Okay? To determine when f prime of x does not exist, what do we look at?
Denominator.
The denominator. Or potentially if we have like some, even-powered roots here. Since we have a cube root, do we have to worry about x squared minus 1 being negative? No. But we do have to look at the denominator. We want to know when the denominator is going to be equal to what? 0. If the denominator equals 0, then we could be undefined, which would not be good. So let's see here. The denominator equals 0, so I set the denominator there equal to 0. I divided both sides by 3 and cubed both sides, so I ended with x squared minus 1 equals 0. Added 1, took the square root, so it's x is plus or minus 1. So there's where f prime does not exist. All right?
All right.
Easy peasy. Not easy peasy. No, it's not. You're right. It's not easy. It's not easy. All right? I'm going to give you guys about 12 minutes to get started on your homework, and I do want you to get started because, A, you're not going to have me at home to look over your shoulder and say, oh, that's right, or, oh, we need to look at that, okay? So I want you to get started now. Take advantage of that. Okay?